on the axis to get an idea from where I'm coming. I run a computational neuroscience lab, and the kind of things that we do are primarily motivated by the science. So we want to understand principles about how circuits support adaptive behavior. But in the course of doing that, we sometimes end up accidentally developing tools, and this could be both on the theory side and on the neural data analysis side. So we do lots of different things, but just to orient you, like what we're going to talk about today, we're going to talk about a very concrete way of doing theoretical neuroscience these days. So the picture looks something like this. Let's say that I have a task that I get an animal to do, some arbitrary task. And I want to understand the circuit mechanisms behind this task. So how am I going to go about it? So I'm going to take my favorite recurrent neural network. I'm going to train it by my favorite means, which could be by supervised learning or reinforcement learning, to do this task. And once I have a trained network, I open the box, I reverse engineer how does it do it functionally by identifying dynamical systems features of interest, how sensory inputs move between attractors, things like that. And this is the form of the experimental predictions that I'm then taking to the brain. Okay? So there's a very long history of doing this successfully, going back to more than 10 years now, to Mattei and Susilo. And we know all of the things that work because they get published in the papers, like we see them at COSYNE in the contributed talks. So we know the things that work. I'm not going to belabor that. What I'm going to talk about today is the ways in which this approach fails, and specifically the challenge of taking this general philosophy into the realm of complex tasks. And I'm not going to get the little rats to drive cars, although that would be cool. The complete task that we're going to talk about today is a decision-making task developed in the Cristina Savin lab. And you might have heard about it before because Carla Goldman was talking about it in the main meeting. But just to refresh for those who just came now, it goes something like this. So a trial is initiated by the animal poking in the center port. They hear a sound that communicates a reward volume offered to the animal, but the reward doesn't come immediately. There's a random delay coming from an exponential distribution that the animal has to wait for a reward. And what it needs to do is to decide, should I stay or should I go? Is the volume of reward that I'm being offered this particular time worth my time? Or if I abandon this ship and try again, am I going to get a better offer? Okay? So that's the premise. The way we read out behaviorally what the animal thinks about the particular reward is by having a small fraction of the trials when no reward is being provided. So the animal has to opt out eventually, and how long it's willing to wait in those trials tells us how much is this particular reward worth it in units of time. Okay? So after a lot of training, the animals are quite good at being sensitive to the structure of the task. So they wait longer if I give them more juice. Good enough. But what's really interesting about this task is that unknown to the animal, there's extra complexity going on. So the world changes. So in blocks of 40 trials, the rewards that are available to the animal are different. So you have mixed blocks with all possible rewards are available, but you also have low and high blocks where only the bottom or the top set of possible options are available. And why is this important? Because I said, like, should I stay or should I go? Normatively, it should depend on what other options are out there. So the opportunity cost, what am I missing out of by continuing to this particular trial? And again, in very nice behavioral characterization of the behavior in rats in a paper that recently came out in Nature Communications, we show that the animals are yet again sensible about their behavior. So they're going to wait for exactly the same volume of reward, which is a 20 in the middle of the distribution. They're going to wait substantially longer in a low trial when it's the best out of a bunch of crappy options compared to the high block when it's the worst out of possible good options. Okay? And this was the example in one rat, but this is extremely systematic across hundreds of animals that Christine gets to train in her rat farm. So it's a very robust tool. Okay, which we just look at the difference in wait time between the two conditions. With the number smaller than 1 means that I'm waiting longer in the low block, which is sensible. Okay, so this is the premise. It's a complex task because it involves dependency structure on multiple timescales. It's also hard for the animals. It takes them 6 months to learn it, and a smallish fraction of the animals never get to learn it. So it's hard by any kind of metric of the work. But we started asking the question: okay, like how could this be implemented at the circuit level? Can we model this behavior in a trained neural network in order to generate hypotheses about how this works? And this is work done by a very talented postdoc in the audience there. And any technical questions that I don't remember, he's going to be the one answering. Okay, so we tried. And we tried. And it was very hard. So this is sort of like with traditional machine learning means training deep RL agents on this task, you get something like this. You get no reward sensitivity, so the behavior doesn't depend on the reward, and no block sensitivity. So no block or context sensitivity. So whether I'm in a mixed block or high block, it's all garbage. Okay. So we tried everything. We tried architecture changes, so like big hyperparameter sweeps, lots of other stuff, and at some point we came up with the more brilliant idea of, okay, maybe we should model the shaping procedure that the animal is actually undergoing in the rat farm, and that finally gave us some okay reward sensitivity, but the other way around. So now the stupid agents, instead of doing the right thing, they decided to wait longer in the wrong block, in the high block. Okay, so this is a good moment to take stock of your life choices. It's like it really felt like banging your head against the wall over and over again. But because we're not allowed to be grouchy here, but by my own rules, I will replace this with a Thomas Edison quote. Basically, we learned a lot of different ways how not to train a deep RL agent in this task. So machine learning did not have answers for us. Like, we tried everything, this was not the way to go. But our light bulb moment came from sort of thinking more carefully about the biology. So we asked ourselves, okay, so clearly experimentalists get these rats to do very complicated things. How do they do it? And to show you the most complicated thing that I could come up with is finally a rat driving a little car. So you can do it. Yes, that's very cool. But how do they do it? So it takes training, but it takes very specific kinds of training. First of all, if you're thinking about the sub-computational elements of what the rat has to do in this awesome task, there's some that the animal brings with him to the experiment. So the ability to see where the target is, the ability to know that if I want to go to reward, I need to plan how to get there. So those are things that we don't explicitly train the animals to do, they just know them. And then there are things that I actually have to train the animal to do, like driving a little car. Okay? So once I've trained the animal on these little pieces, then behavioral shaping engineered by the experiment with the concrete task ending in mind will put these pieces together in the right way to finally achieve the awesome rat driving behavior. Okay? So we try to do exactly this thing in our model. So this will be a little bit of an nitty-gritty, how does the architecture work, but it's important to understand the rest. So again, inspired by anatomy, we split our architecture into two elements which we kind of loosely associate to orbital frontal cortex and the striatum. And both of these subunits, which each of them are modeled by a bunch of recurrently connected LSTMs, because we have really long time scale dependencies, get the inputs that tell you about the offer, am I offering you 5 microliters or 8 microliters. Then the OFC's job, based on the previous literature, should be to report something like inference about the state of the world, so beliefs about in which kind of block am I in. And the striatum is the acting agent in the world, so it needs to report what should I be doing. So what should be my policy right now, and what should be the values of different states, because we need these sort of things in order to train the system by deep reinforcement learning. Finally, inspired by the architecture of Jane Wang on MetaRL, the entire system receives as inputs previous actions of rewards, because what I did and what came out of it is informative for which kind of state I am in and what should I do about it. Okay? So this is the general purpose, the general form of the architecture, and then we sort of made a mini version of exactly the task that the animal is doing. So we get a trial initiation that kind of happens not decided by the animal, but rather self-imposed, directly imposed. We get a sensory stimulus, and then sort of the rest of the job unfolds the same way as the animal. Okay, so as I said, the architecture was motivated by biology, but the architecture on its own was not enough. We need to sort of get this sort of training procedure curriculum working right. And to do that, we had two important components. So one was this, what does the rat know before we start the experiment part, which we trained explicitly as a collection of little tasks. So we trained the network to know how to keep information memory, how to count time, to know how long have I been waiting, how to integrate information over time, and how to do inference. So these are outside of the task context, and they're trained with supervised objectives. So they're sort of again, trying to mimic the kind of experience that the animal brings with it to the experiment. After that, we essentially mimicked one-to-one whatever Christine does with her rats in the rat farm. So the entire shaping procedure that the animals undergo. So this is sort of being intended to put the pieces together in the right way. And again, a technical detail a little bit, but it's kind of important. So these tasks, these auxiliary tasks that we've introduced, which we call kindergarten tasks, because they're teaching you how to behave in the world, have their own output heads, and then again, they're trained in the initial phase of the process, but they also continue to regularize the deep reinforcement learning agent throughout the learning process. It's not clear that this is strictly necessary towards the end of training, but this is what we did. So, yes. Good. And the rest of the learning objective is what the meta-RL thing would do. So it's standard. We haven't done anything interesting there. But after working all this hard, we finally got something that looks sensible. So this is one example RNN and one example rat, just as a reminder that the pattern is finally the right way around. And although it's it reproduces the reward sensitivity, so it slopes up, and the context sensitivity as it then moves as a function of the color, it also does fine scale stuff that that go beyond those core characteristics. So if you see both in the low block, the differences, the shifts in how long you're willing to wait are much bigger than relative to for the red, so for the high block. And that's a property of an asymmetry that is inherited from this task structure, is an optimal thing to do. Animals do it, and our funny agents do it as well. You can also sort of unfold this over time, because we have an explicit readout from the OFC chunk of the architecture of what are the beliefs about what kind of context I'm in. I can plot that for the recurrent neural network. And Christine's paper has a behavior model that tries to infer the same thing from the behavior of the animals. And they're not perfectly identical, but sort of they share a lot of qualitative features. So we're finally getting in a regime where we're kind of rat-like enough that we're feeling good about ourselves. Not all of the recurrent neural networks learn, but neither do the rats. So I think that this might be potentially an interesting way of also exploring across animal variability. Okay, so what this is good for? So first of all, we are actually getting more reward. So these stupid strategies that I was showing before, which are the outcomes of just doing the task from the beginning with no shaping, or introducing shaping but without doing the kindergarten part of the process, those are suboptimal strategies. They get you less reward, but they're really salient, easy to do ones, and sort of like the optimization procedure of deep RL will sort of like end up with these solutions more often than not. Again, like, I've already said this before, but our approach is the only one among the ones that we've tried that actually mimics the animal, the key features of the animal behavior. So it's not only that you get like poorer computational solutions, they're so animal-unlike that they're not any good as hypothesis-generating processes for the brain. Like, we can also try to open the box and sort of like look a little bit of what's going on. And I hit all of the details of how this works, but any recurrent neural network has a kinetic energy. You can optimize brute force for local optima of the kinetic energy that gives you slope points in the dynamics. And then you can brute force some more, kill a lot of trees, and sort of like get a pretty like comprehensive characterization of the function. Like here I'm only plotting the number of slope points that the networks have at different stages of the learning process. And what's kind of interesting is sort of like, with all of these like randomly initialized recurrent neural networks, you always see a lot of stuff happening very early in learning, and then sort of like the task relevant part of the component tends to be like small relative to everything else. But here, if you're looking at the magnitude of the weights, and we're going to look at the dynamics in a second, there are like really big changes in the network that happen as a result of our kindergarten procedure. So this is a really strong inductive bias that puts the network in the mood to learn these kind of tasks. And that's important for getting the solution. Again, sort of like for the dynamical systems part, like you really see that what's going on under the hood is we're building this rich dynamical system repertoire that then we can exploit or sort of like pick the right bits in order to actually do the final task. And that's true both in the striatum and in the OFC, but very strongly in the OFC. So it's like a really important piece for the inference part of the process, which is kind of critical for, mission critical for getting the context sensitivity. Okay, so we can look into more detail about, okay, what's the picture like? I told you that there are like fancy dynamics under the hood with attractors and stuff, but I didn't tell you how it does it. So unlike the Manta Esosilo or all of these like kind of examples that you know as the poster children of opening the black box that are super interpretable, this is not quite as nice, and it's not the kind of thing that you could have come up with a priori. So this is not, like, if I had to engineer a system to do this job, this is not how I would do it. But it has interesting structure. So here we're looking at the kinetic energy landscape, and I can put the arrows on so you can actually see what the network is doing over time. And what you have here is a bunch of different dynamical systems features. So you have a line attractor, a saddle, and a point attractor, and these are kind of partitioned in different belief states of the animal. So because I have an explicit readout, do I think I'm in block high, do I think I'm in blocks mixed, or do I think I'm in block low as a function of where I am within my later activity state space, I can partition the entire space into I'm pretty sure I'm in this versus that kind of region. And like these different dynamical systems features like aligned in sort of like different chunks of this space. So I'm using a line attractor to represent something about the high part of the structure. I'm using a saddle point in the mixed region and a point attractor for the low region. And although there's a little bit of a cross-network variability of how it does it, this is not a universal task where no matter what you do, you end up with exactly the same solution. Most of the solutions look like this. Okay? So this is robust enough across networks and across wiggles that we trust this to be a signature that we can go and test in the experimental data. So we have another block, and we can ask, okay, so how does the actual decision get made? This is a little bit trickier because this network gets input from the OFC, and that input is condition specific. So I don't have a single way of doing the dynamics in general. I have a condition specific way of running the dynamics. It's a lot simpler in some sense that I always have a single fixed point, and here instead of the color showing the kinetic energy as I was doing before, now the color shows what's my probability of staying or going, okay? So the blue region is when I'm saying bye-bye and I'm going to the next trial. So what we're seeing here is that how close are the fixed points relative to that region changes as a function of my beliefs about what kind of block I am. So I get to, like if you project in a one-dimensional space, the attractor like shifts as a function of beliefs, so I stay longer in a blue block versus rather than the mixed block. And again, like the degree of shifting is such that the blue changes are bigger than the red changes relative to the mixed. Okay, so this is the mechanism that allows me to change my mind about how long am I willing to wait as a function of which kind of block I think I hit. And this is sufficient to explain both the structure and the asymmetry in the behavioral results. Okay, so we're almost done. A few short take-homes. I think sort of like the most important for one is that the brain is not tabula rasa. So it's not a blank slate. Like whatever learning we as the experimentalists do to an animal happens on top of a lot of extra pre-existing structure, and that reflects the statistic of the worlds and the experience of the animal. And like maybe if we're doing universal tasks or really simple tasks that have a very unique solution that they're not hard to optimize, and no matter what you kind of still get it, that those are nuances that don't matter. But the moment where you actually start training animals on tasks where the previous experience of the animals and their skill set matters for their ability to learn the new task, if you're not modeling that part of the experience, you might get in trouble trying to generate predictions. Okay, and sort of like, it's not that it takes longer to train or something like that. It's like the actual computational strategies, what the policy of the animal ends up being, might be qualitatively very different. And that puts you in the, oh, this is nothing like the animal, I don't know what to do kind of scenarios. Okay? I didn't emphasize this enough, but the key ingredient for making this work is identifying the bits of computational pieces that are strictly needed for the animal to perform the task. So the ability to take complex tasks and decomposing them into bits of elements that I can train independently with simpler means is kind of the essence of the solution here. Yes, so now, although we haven't done this yet, we're sort of at the point in time where we have the data, we have like very clean predictions about what we should be seeing in the data. So we need to go to the other workshop to figure out how to get the best estimates of flow field that we can with the data that we have available, and then we should be at least either prove or disprove this hypothesis, okay? This is where we're at with the science. I want to say sort of like a couple more general things about the philosophy of the approach. As is the case from here, like I'm presenting you with one anecdote. Like the Mantia Cecilia was a pretty anecdote for how to do context dependence. I present you with more complicated anecdote about how to solve this particular task. It's really hard to say, if I take these ideas to your task, or your task, or your task, is this still gonna work? But it's kind of hard, like, we would want to do that. We would want to have some supplementary in the paper where we do this for 5 extra tasks. But maybe David wouldn't, but I would. But sort of like, it's like, what kind of task? Like, I think as a community, it might be nice to have like a compendium of, look, this is like a collection of tasks that I would like to sort of like have reliable signatures for, maybe make it into a competition. Like, define concretely computationally what the tasks are about, and let's fight it out. Let's see what kind of tools work. And the other thing is, something that David Susilo was also mentioning, like we have this idea that in the early training, in the kindergarten part of the task, what we're doing is really like making rich dynamical system features that somehow we can exploit later. But like we're taking individual snapshots of the dynamical systems profile of these networks. So it's really hard to say, is the feature that I've learned in kindergarten at time t actually the feature that I get to use in task deployment time many time steps later? So it's something that we've been trying to work on, so I'm trying to sort of like track the evolution of these dynamic features over learning. If you want to hear that, there's an extra preprint by Owen Marshall that goes into that in a little bit more detail. Yeah, this is my group. We need to thank Christine for all of extraordinary collaboration in the course of this project and inspiring all this work. The Rats for doing the hard work, and the HPC for doing the rest of it.